Good afternoon, ladies and gentlemen. It's an honor for me to be part of the UAE delegation talking about some of our initiatives at G42. This is one of the important initiatives we've been starting recently to support marine economy or marine ecosystem conservation and efforts. We named it One Ocean Cloud. So G42 is a cloud computing and AI company based out of Abu Dhabi, and it is working on several domains of AI and cloud computing in different fields like healthcare, geospatial, mobility, financials, and all those things. So what is One Ocean Cloud? So it's a dedicated cloud for ocean conservation, which aims to support blue economy development, centered around these 6 initiatives on marine data integration initiative, which combines data from multiple sources, spatial and temporal monitoring of nearshore and offshore environments using remote sensing and other technologies, food security, nutrition, and health in terms of understanding the food potential of the seas, entrepreneurship support to support new companies that could utilize all these data resources and build new ventures. Advanced Marine Genomic Studies program, which is the most important program in this initiative, which is trying to establish an enhanced digital marine biobank of ocean species around the world. With this, we would like to also enhance the training programs to support utilization of these data sources. The number of fields that we use in these initiatives, and also some fields which benefit from these things. So the prime components of these things are sensing, communications, computing to a larger extent, aquaculture for food security and applications, genomics for characterization, and a bit of marine biotechnology to understand or develop new products or new components there. So what exactly is G42? It's growing into a wider ecosystem, starting as a cloud computing and AI company. Now, when you say AI, you can do pretty much a lot of things, and that's what G42 is trying to do. It's growing significantly in a number of fields, be it geospatial at Bayanat, where I come from, then healthcare, looking at human genomics and other genomics programs, financial, looking at fintech and other things there, basically. So the cornerstone or the key component of all these things is the cloud, the background cloud that supports all these initiatives. So as I said, based in Abu Dhabi, G42 is a leading AI and cloud computing company dedicated to developing and implementing scalable technology solutions on the cloud. So with the aim of achieving the One Ocean Cloud, this is a very key initiative. We are looking to support the UAE's climate efforts, basically. Within this thing, 3 subsidiaries of G42 will be involved. Bayanat, which is a geospatial AI company. G42 Healthcare, which was primarily looking into healthcare, but genomics is a very significant part of this business unit. And that's the part which we will be leveraging a lot. G42 Cloud, of course, because you need to host all these things in one place and develop applications on the top of that. So, as I said, Bayanat is the geospatial company dedicated to serving a number of end-use applications on mapping, surveying, both on land and marine environments. Bayanat was the key trusted provider and strategic partner for several government initiatives, organizations or agencies in the UAE, and also the armed forces. For G42 Healthcare has been growing significantly, supporting the Human Genome Program of the UAE, and also establishing the Omics Center of Excellence for the region's largest and most advanced omics facility to work on large-scale genomics programs. And cloud has been growing significantly to become the largest and most powerful cloud platform in the region. So this combination of the partners here is going to combinedly work together to generate this huge One Ocean Cloud initiative. We're also working with international partners like OceanX on a wide range of marine topics, and also with Environment Agency in Abu Dhabi. So I'll skip this a bit. I already spoke about Bayanat. Bayanat is a geospatial artificial intelligence company which operates in a number of fields, including geospatial AI, and which has byproducts in autonomous mobility, for instance, autonomous vehicles and all those things. And we also do large-scale mapping, 3D mapping, and all those things. So the Healthcare Omics Center, I'll have my colleague Dr. Weil joining us in a bit on the stage, and he'll give a bit more details on the Omics Center of Excellence and the genomics activities healthcare is working on. But just to mention, it's like G42 Healthcare Labs, or the Omics Center of Excellence, is one of the largest genomics facility probably in the world, or at least in this region. And this is the key point to support a large number of initiatives, be it the Human Genome Program or the ongoing plant genomics and eventually animal genomics and marine genomics programs that will be starting. The cloud, as I said, is one of the largest cloud in the region and is strategically placed between East and West to kind of fill the gap that there exists in this region. And one of the key concepts that was championed by G42 Cloud is the sovereign cloud concept, which is to provide dedicated cloud facility for government solutions within the country and clearly certify for secure use of the cloud. So, coming back to the One Ocean Cloud, it's an ocean research computing infrastructure powered by G42, dedicated to support large-scale exploration programs. So what we'll be doing here is we'll be trying to create a very large digital marine biobank. Probably you've seen vials of species, in those vials in natural history museums and all those things. The modern version of this biobanking is the digital biobanking with the DNA. So once you have a physical biobank and a digital biobank, which you can utilize to support a large-scale data lake, you could do a lot more things with that thing. So this is where the cloud part comes into the picture. So we are developing a large-scale comprehensive data lake to support multiple data sources, be it sensing coming from satellites, drones, ROVs, and all those things. You have these underwater videos, hydrography maps, temperature measurements at different locations, be it salinity measurements or whatever, or habitat maps, for instance. Combine that with genomics data or species data, species spotting, for instance, from underwater videos and all those things, or DNA spotting from underwater, from water samples and so on. You can create this huge ecosystem that can give us a lot more clues about what's the status of the marine environment. So that's where the large-scale AI development opportunities come into the picture once we figure out a way to put all these data sources together and start providing the tools to develop these analytics capabilities. Of course, once you have all these things, then education and outreach becomes much more easier compared to what it is now. So this is a wide top-level hierarchy of the architecture we are trying to work on, where we have data sources stacked in one side. You see, it's completely diverse range of data sets we are talking about. You have images coming from satellites, images, video streams coming from underwater videos, genomics data, temperatures or hydrological parameters, and all those things stacked up in one side. And then you have the platform where you can develop analytics capabilities based on these data sources. And we have the algorithms part where people can develop their own algorithms and put it there in the marketplace for easy analysis and so on. This is all supported by one cloud, the dedicated cloud, which provides computing, storage, network, and the platform. And this entire architecture is expected to support a very, very large initiative. So our aim is to develop this comprehensive marine biobank. We'll talk about this more while we're talking with Dr. Weil. But so building a reference data set of the genomics for as many species as possible. I cannot say all, but as many species as possible is going to give us a lot more information. There are so many examples of how genomics or DNA evolves to adapt to changing environments. In this case, changing climate, for instance. The oceans are warming up significantly. The environment is changing because of anthropogenic pressures from us, and the climate change is really affecting various parts of the oceans. We need to see how the traits in the DNA are changing and evolving, and for that, we need to set up this database and start monitoring that thing. So once we have this data collected, there's a lot more analytics we can develop on the top of that. A lot of insights we can develop. For example, population estimation. Wherever the species goes, it sheds DNA. So by collecting samples and understanding the DNA, we can get a lot more characteristics of the species we are looking at. For example, if you're specifically targeting a specific fish that is going extinct, for instance, we can see where it's going, which habitats it's surviving in, and how those habitats are changing. And based on that, we can actually come up with better mitigation or management strategies in a way. So we want to rely heavily on this concept of environmental DNA. So all these things used to be so expensive let's say 5 years ago, but with new technologies that are coming up, things are becoming cheaper to do these analytics. So the concept here is that you or me or us and any species in the world, wherever it goes, we keep on dropping our DNA. If we can analyze those samples of those dropped DNA traits, basically, we can get a number of clues about what is happening there. So that's exactly what we call as environmental DNA. For example, in the marine environment, we collect few water samples, and based on those water samples, we can deduce which type of fish came to that location, for instance, how many types of species came to that location. And by understanding what the environment is, what the habitats are, we can deduce a lot more information about that species and how it's feeding, where it's breeding, and all those things. And from that, we can, for example, we can create go-no-go zones for fisheries. For example, to be extinct species is coming into a certain region, and we can identify the trait of that from the sample. We can tell the environment agencies to enforce a no-go zone there to make sure that survives. This is one example. But you can build a lot more applications like that on the top of that. So this is going to be very crucial as we collect more and more samples and build the story of this environmental DNA. A lot more information. We can start producing maps of zones of different species and different environments and so on. So with that, what we can do is we can collect these water samples in different places, use those databases that are being created for machine learning on the top of that to understand which species come to which place or the characteristics of the species. On the other side, we have the sensing part, the acquisitions from satellites, drones, or whatever, or ocean measurements will give us information about the details of the habitats, the details of the species, and so on. And if we combine that information together, this entire ecosystem provides us a huge resource to understand the ecosystems in a better way. So that's what we want to achieve with this entire One Ocean Cloud concept. So with that, I would like to invite my colleague, Dr. Weil, onto the stage. And we would like to have a very short discussion and open up the stage for further questions.
Thank you very much, Prashant, for the introductory about what we're trying to achieve. The way I perceive this is we all live in an environment. We might be healthy, but if your room is dirty and you leave that room, people don't know what's happening to your house. So we can all sense what's happening to the fish, count them. An unhealthy fish does not necessarily mean an unhealthy environment, but vice versa. You might have an unhealthy environment whereby you have an unhealthy fish. So one of my colleagues was asking me, what are you trying to do? I told him maybe the Instagram of fish and identifying how the fish look like. a bit of CSI and a bit of Instagram together. Is it expensive, do you think, in terms of data, not money? Would this cost us a lot of data currency?
It's probably much cheaper than what we're losing. That's what I would say. No, it might be a lot of data there, but if you're putting that together and actually and giving better analytics, we're probably going to gain more. And that's how I want to see. Even if it's some investment in the beginning, we are going to gain much more than that. So based on that, I want to understand a bit more also on the environmental DNA concept. This excites me a lot whenever I see that. It's like this entire concept has so much potential. That's why we left it as a cornerstone slide here. Dr. Weil, can you please, for the sake of the audience, can you please explain a bit more on the environmental DNA concept, how that works, what it's going to generate, and what are the wide possibilities we have from this concept?
So so the environmental DNA concept has been going on for many years now, about 20 to 30 years. Probably 2002 would have been the 20 years exactly now. And if you think of us today, we're in a big pavilion. There's probably around 4,000 people of us here, each of us shedding DNA. Some of us might have a virus, an infection of some sort or other. For us to test and screen every single person for SARS-CoV-2, which is what we were doing 2 years ago, we could have asked for a test coming into this environment and a test out. There are other methods whereby you can test the whole group by taking a single sample. For example, if we look at this, I might consider taking a sample from the effluxing air, from the air coming out from the ventilation systems. And it's the same, and test it and quantify it to estimate the total number of people who have one type of infection or one type of disease or one type of anything else. The same concept is being used in wastewater to estimate the number of people in a given population with SARS-CoV-2 or poliomyelitis has been on the news recently, whereby you estimate large populations, large number of people, utilizing a single test, which makes it very cost-effective for governments to assess risk or potential benefit. The US has been doing this. Australia have been doing it in marine environments much more before us. And for example, you have Asian carp species in the lakes, in the Michigan lakes, which is an invasive species that could significantly affect the other fish species. And if you have one, if you identify one, it's an indication of an invasive species which might affect significant economic effects on the environment. But to catch that single fish by chance is a lot of effort and cost, because you'd have to be using particular techniques to identify the fish, whether it passes by, whether or not. So what they've established there, they actually use environmental DNA, whereby they take a sample of water and very cheap actually, they take it and they specifically look for the DNA which this particular species of fish secretes or releases on the environment, and that in itself becomes an indication. If they identify the DNA, immediate action is taken to identify even further risk. The Australians have been doing it again for invasive species, and with the increased mobility of humans, animals, plants, the globalization that we face at the moment, there's a lot of invasiveness happening, which might affect any of our species in any of the waters. And unfortunately, the environment doesn't work in isolation, it works as a whole. So one event might lead to consequences elsewhere, regardless of how small or big that is.
Yeah. So for example, if we want to utilize this concept to estimate stocks, the entire fisheries service concepts we have now, where people, agencies go in these ships, catch fish, collect their otoliths, break them, measure those things, get the ages, collect a large number of samples, and based on that samples, they create the statistics and get an estimate of fish stock, ages, and all those things. How easy is it going to be with this concept?
It's a lot easier, and probably a lot cheaper as well. So the methodology of the gold standard still remains to identify species, is to capture it and document what it is, supplemented nowadays by genomics and omics.
Okay. So that I think is the biggest opportunity now. So what changed in the last 5 years? Let's say, is it the cost of the equipment, or widespread technology, or what is changing recently that's going to help us in this initiative, for instance?
You're a data analyst. I think it's Moore's law that we're following at the moment, whereby the cost of performing this analysis and the speed of it has changed significantly, in particular with the availability of supercomputers that we have at the moment. I like to say that previously we had real intelligence, but now we're supplementing real intelligence with artificial intelligence,
Yeah.
whereby we have a hypothesis that we can test in seconds nowadays. It doesn't take ages to design your DNA primers, to test the hypothesis. And I think me and you, we had this discussion, why don't we go and try it on a fish tank in one of the aquariums
Yeah.
to get a better estimate. So to do an experiment like that previously would have been very costly and very difficult. Nowadays with the supercomputers, it does generate a lot of data.
Yeah.
And you need a lot of number crunching that was not possible 15 to 20 years ago.
Yeah.
Nowadays we generate 90 gigabytes of data from one sample.
Yes.
That gets analyzed in about 2 to 3 hours.
Yeah. To add to that, its sensing technology has also significantly improved. There are a lot more satellites acquiring data all over the world. A lot more data is flowing in. Lot more capabilities are being developed in the sensing technology as well. More better sensors are coming up. So, for example, you have these hyperspectral cameras which are getting images in hundreds of bands compared to few. If you take your regular camera, you have 3 bands, the red, green, and blue. But if you can image in hundreds of bands in visible, near infrared, and shortwave infrared, you can characterize the entire environment in a better way. You can actually distinguish between different habitat, species, and so on. So that combined with this is going to make a very, very significant difference now, and so on. The other thing I wanted to ask was, it's like in terms of the capabilities, what would be required to take this data and get insights out of that? What is your experience and the type of analytics, type of insights we can derive from this large amounts of data?
So it's all about storytelling. And you need a continuum of events to understand cause and effect. And looking in isolation at just one event without understanding everything happening at the same time would not necessarily lead us to the right conclusion. So it might be a volcano explosion somewhere, leading to the change in sulfur amounts in an ocean and migration of particular amounts of fish. Previously, you wouldn't have been able to identify all of these going together. But now with the amount of data that's being generated continuously, even from social sciences, not necessarily from big organizations like ours, of events, and looking at them in a holistic manner, whereby identifying significance, whether if we take the classical methods of epidemiology and looking for a single effect, a single event leading to an outcome, we can do that with multiple events. So the previous analysis of variances is now done at thousands and thousands and thousands of variables to try and identify a single outcome that we would have never seen before.
Yeah, that's where so the more data we collect and the more better algorithms we can develop, the analytics will become much more easier to handle, and we can have probably better insights. With that, it's like I would like to ask the audience if you have any questions to Dr. Weil and me, and see if we can look into some other discussion. So your question is, how big are these data sets now? What would be the size of data that is acquired through one environmental DNA sample, for instance?
So it depends on the method you use. You can make it as small as you want or as large as you want, and depending on the resolution that you want to get into. Previously, we used to use something called mitochondrial DNA, which wouldn't generate as much data as we do at the moment. And we have to remember that the ocean is not only full of mammals, or you've got a lot of different species. So you've got the fish, you've got the flora that the fish have. So each, or the species, you've got the underwater plants, you've got the algae, so there's a lot of DNA floating. Getting the right amount of data without burning your computers is a fine art.
So what's the rough average volume of one sample, for instance, you know?
So if you
We're
have
talking about megabytes, gigabytes.
no, we're talking about gigabytes. I'd probably be looking at the range between 3 gigabytes to 90 gigabytes.
So that's one sample. So
one sample.
how many samples would you need, for example, to characterize an area of UAE waters, for instance?
So it's the problem is, remember that the water is not constant. So you've got currents and flows, and so there's a lot of inconsistency here.
So dozens of data sets.
Correct.
No?
So
Okay.
you're going to need from the same, to understand just one location, we'd need to have repetitive values and repetitive numbers and repetitive measurements. And following that, then you extrapolate to try and see how much that area, how much that small sample, how representative it is of the area that you're doing.
Yeah, that's the reason why cloud is important, because that's a lot of data. Now, when you're talking about images, now I can attest to that. Now, for example, if you're mapping 1 square kilometer of area, 1,000 meters by 1,000 meters, which is a million pixels, pixels if you take 1 meter pixel. But if you're talking about a 10 centimeter resolution image, you're talking about 100 million pixels. And if you're talking about 3 bands, that is 300 million bytes. And if you're talking about 100 bands, that is 3,000 million bytes. That is 3 gigabytes, basically, you know. So that's the volume of data we are collecting for a square kilometer, for instance, you know. So if you're trying to map several areas and so on, different types of data sets, you also have to look at other data sets like temperature measurements or salinity measurements, conductivity measurements, and all, or CTD measurements, and all those things which are routinely taken in marine studies. Or the hydrography, for instance, the 3D models of the sea floor and all those things at different resolutions. These are humongous data sets we are talking about. And if you're combining that part and the genomics part, that's going to create a huge ocean of data. That's where cloud is going to be very, very important.
So if I ask you, Prashant, because I'm having difficulty visualizing what you guys do in sort of with all of your coding and black screens that I understand little of, is how are we going to integrate our maps and our data into your maps? How difficult of a task is that?
The key point that is attaching everything to a certain reference is the geospatial location. For example, you're collecting this environmental DNA sample and saying that, let's say, the easiest fish species we know of, tuna. You say that tuna, this year, we found that tuna is coming to this area, and then we are estimating, let's say, 100,000 tuna fish per square kilometer that we estimated as a stock in that region. We collect this data every year. So we have a time series of that thing, okay, at that particular location now. You can create that maps of different locations. And now we see what is happening with the environment. What is the temperature, water temperature, how is that changing over time? Salinity, how is it changing over time? Or any pollution that is coming on, or the habitats that are there, you know, the mangroves, for instance, close by, because mangroves are breeding spaces for most of the fish species, right? Or corals, for instance, and all those things. We create that other set of data sets which tell about the environment, basically, or the conditions of the sea. Now, if you look at the time series, now if you see that the amount of tuna you're finding at that particular location is going down, which means it's not coming to that region, it's not surviving in that region. And now you go back and check what is happening to the habitat. What happened? Is the temperature increasing, which is affecting the corals, for instance? Or something else happening if there's another invasive species coming in, because you need to go back to your database and see what other species are increasing in that region. So all that analytics can be developed by using the geospatial location as a reference, as an example, you know. The number of things we can do, you know. Way back in 2017, you know, it was called as the Godzilla year somehow, because now it's the temperature differential was so high that year that big chunk of almost 70-80%, or if I'm not underestimating in a way, of the Great Barrier Reef got bleached. But then that year, we figured out in the UAE waters, one of the coral reefs there was thriving and was healthy. Why is that happening? Because there was a symbiosis between a certain macroalgae species and the polyps, coral polyps. The macroalgae was protecting the polyps against this temperature differential. Now, this is adaptation to changing climate now, right? Now, you go and check what are the DNA traits there. You get a lot more insights from that thing, right? Not just simply saying that this is surviving. Why is it surviving? You need to get answers from that thing. So this is where the analytics is important. The insights we can derive from that is important, you know. That's where this initiative will stand up and can create more value to this entire ecosystem.
Okay.
Any other questions? If not, thank you very much. Thank you,
Thank you
Dr.
very
Weil,
much.
and
Thank
thank
you.
you for
Thank you.
being here.